Alright. Ooh, make my screen dark. Okay. Got the recording going. Yeah, we'll do lecture first and then we'll go over all your mini homework problems that you have questions on. And just a reminder, you know you have all the answers in the back, so oftentimes it helps when you get stuck on a problem to just look in the back and see if you can reverse engineer what they were after. Because typically you'll be asked like 3 problems of the same type, so if you get stuck on the first one, you can reverse engineer it, then use the next 2 to make sure you understood.
Okay.
So a common strategy I used all the time back when I was going to school. Open up the book. Okay, so today we're doing our trig review following what the book says. So following the book, first thing they introduce is the notion of a radian, which we already have talked about. And that's not great.
Why are you guys throw away?
So I don't want to walk over to the garbage can.
Just throw it. What are you gonna?
There we go. We got something. Okay, so here we are just looking at a quarter of a circle. All we need. And when we've got some angle on the circle, here it is. Here's our angle. We call this angle theta. This is r, our radius, or that's r, our radius. What is this distance from here to here if our angle is in radians? And we call this s. What's our arc length?
It's the measurement in radians except for
Did we forget? Let's go back to what a radian is. How many radians are in a circle?
2. I'm sorry. 1.
No. There's roughly 6.28. How many radians are in a circle?
2 pi.
2 pi.
Oh.
2 pi. That's a lot. 2 radians look something like this. Here's a 2 radian angle roughly. 3 gets you almost all the way around. Okay, so let's recap how we talked about radians. First off, I said here's a circle with radius r. And I asked you, how much distance is it all the way around the circle?
2 pi.
2 pi r. What is the circumference of the circle? C. What's the circumference of the circle? What's the equation for circumference of the circle? 2 pi r. That is the distance all the way around the circle, circumference. What's the distance halfway around the circle?
Pi r.
Pi r. What's the distance a fourth way around the circle? Pi halves r. That's the distance. So the amount of radiuses, the arc distance one radius goes, we call 1 radian. So if it's 2 pi radians to get around the circle, that means the distance is 2 pi radiuses. So the angle is 2 pi, the arc length is 2 pi r. Are we following that?
Yes.
I think so. Think so? Okay. So come back to this then. Here's my angle in theta. Or here's my angle in radians. Theta is my angle in radians. What is this distance right here?
Pi.
Let's pretend that this angle is exactly pi thirds. What's this arc length?
Pi thirds radians.
Pi radians is an angle. Just like degrees is an angle. Radians, we're talking about angle. I want a distance now. What is the actual distance? How far will I travel if I walk all the way along this angle?
Would you just say pi
Pi
thirds?
thirds times r.
Pi thirds is not a measure of distance. Hey, I want you to go pi thirds that way. Pi thirds what? Pi thirds radiuses. Okay. Radius is a unit of distance. Look, if the radius was 10 meters, then now what is this distance right here?
Pi thirds times.
10 pi divided by 3 meters. That's what it is.
Yeah.
Right? You following that?
Yeah, makes sense.
What's the angle here though, if this is 10 meters?
Pi thirds.
Just still pi thirds radians, right? Doesn't matter how big or small you make a circle, an angle's an angle. It's the arc lengths that change. And the arc lengths change proportional to your radius. So, now, if you don't know what this angle is, and I just put in a theta here, what's the arc length?
Just theta r, right?
Theta times r, perfect. That's the beauty of radians. If you have the angle in radians, to get the arc length, you just multiply by r. That's why we love radians.
Okay.
Going from the angle to the arc length, it's as simple as multiplying by r, or going the other way. If you have the arc length, and you want to know the angle, divide by the radius.
Just to clarify, radians is only an angle measurement?
Radians is an angle measurement.
Oh.
So 1 radian is equal to 180 degrees, not 1 radian, pi radians, is equal to 180 degrees. Same thing. Now, how much is 1 radian in degrees?
1 radian?
1 pi.
Yeah, quick conversions, something that you've done all the time. If I want to convert the units, I need to multiply by 1. That changes the units. So I'm going to multiply 1 radian, and now I'm just going to multiply by 1. I'm going to multiply by a special one up here. So if I multiply this by 180 degrees over pi radians, you see how this is still 1? That's the exact same angle. The radians cancel out, and what are we left with? We're left with 180 over pi degrees, whatever that is. You can plug that into a calculator to get a rough approximation. Should come out roughly 57.3 degrees. So 1 radian is roughly, it's a little less than 60 degrees. Make sense?
Yeah.
And then you can do it the other way to figure out what 1 degree is, and you'll see that 1 degree is roughly 0.0017. Is that what it is? No, it's way too small. 0.017. Radians. And so you can convert back and forth between these things if you need to. Good? Okay. So now how the author introduces the 6 trig functions and their definitions. We already know the 6 trig functions, but we'll see how the author introduces it. So we've got some circle. It's going to be completely equivalent to the way that we define it. Pick some angle. Here's our angle. So here's theta. Drop down, and we make this right triangle. Talk about the coordinates here. Coordinates of that point, we'll just call x, y, which means this distance right here is x, this distance right here is y, and we call this the radius of the circle. And so now, remember what the definition of cosine was. What's the cosine of theta? It's the x coordinate on the unit circle at that point, right?
I don't remember that.
You don't remember that? Your unit circle. Everything you were plotting was assigning cosine values of those angles. So you plotted the angles, and then everything else you were doing, all the x coordinates, you were plotting the cosine value of the angle at that point. And all your y coordinates was plotting the sine value of the angle at that point. Sine gives you the height, cosine gives you the x.
So cosine theta gives you x.
So this x coordinate right here, if r is 1, then we know that x is equal to cosine of theta, and y is equal to sine of theta. Yeah. If we scale this up to r, then these are just r cosine theta, r sine of theta.
Is r times cosine theta?
Yes, sorry. Times.
Okay, so I'm sure it was like a new term.
Yeah, not a new function. So if I scale up my triangle, make it twice as big, that also makes this x twice as big and this y twice as big. Yeah. So that makes sense?
Yeah.
Rework these. What do we get? We get cosine of theta is always equal to x over r when you divide both sides by r. Sine of theta is always equal to y over r when you divide both sides by r. Make sense? Mm-hmm. Now that's how the author just introduces their definition. It says cosine, he says, look at this picture. Okay, cosine of theta equals that, sine of theta equals that, tangent of theta is equal to, I don't know if he says sine over cosine or if he just lists it as the sides. He just lists it. So he says tangent of theta is equal to y over x. And let's see, next we're going to have secant of theta is equal to r over x. Cosecant of theta is equal to r over y. And then cotangent of theta is equal to x over y. Just the reciprocals of all these. Now the way we defined it, we defined tangent of theta to be sine over cosine. And we showed it still gives you that exact same thing. Yeah. And then we defined secant to be 1 over cosine. So no, secant is just a reciprocal of cosine. We defined cosecant to be 1 over sine. Notice it's just a reciprocal of that. And we defined cotangent to be 1 over tangent. Notice it's just a reciprocal of that. So all our definitions, how the author's coming at this versus us, completely identical, just changing names. Make sense? Mm-hmm. Okay. So we've already talked about the values of some of these functions. Now let's get comfortable graphing some of these functions. And yesterday we already graphed the sine and the cosine function, right? Yeah. So we'll kind of throw those up here real roughly and then continue to do the other 6 trig functions. So you've seen them all. So call this 1, this -1. We'll call this pi. We'll call this 2 pi. Here we have 3 pi halves. Here we have pi halves. Here we have minus pi. Here we have minus 2 pi. And then minus pi halves. And minus 3 pi halves. Minus 3 pi halves. Nothing, you get the picture. Okay, let's start with plotting sine of theta. And we'll call this the theta axis. We could also call sine of x, call this the x-axis, doesn't matter. It's just a label. Okay, so let's do this real quick. Let's start at 0. What is sine at 0? What's the y-coordinate on your unit circle at 0 degrees, or 0 radians? 0. So sine starts right here. That's the first point on sine. Okay, at pi halves, what's the y-coordinate? 1. At pi, what's the y-coordinate? 0. Wow, that is a terrible placement. I'll clean some of them up, but we'll get real lazy here in a sec. Okay, 3 pi halves, what's y value? -1. 2 pi, what's y value? 0. And we can go work it backwards as well. What's the value at minus pi halves? -1. Value at minus pi?
0.
At minus 3 pi halves?
1.
Minus 3 pi halves is the same thing as 90 degrees, right? We've gone all the way. And then 2 pi back to 0. So try to get a very rough sketch of this thing. It waves like this. Call it the sine wave. And we'll be working a lot with sine waves. Okay, so there's our sine function, right? Now, the one that we typically like to graph with sine, so here's sine, but the one we also like to graph with it is 1 over sine. 1 over sine is what cosecant is, cosecant of theta. So we're going to do the reciprocal of each point. What's the reciprocal of 1? What's the reciprocal? If I take 1 and I flip numerator and denominator, what am I left with? 1. Right? Here's 1. Now flip the reciprocal.
No, just 1.
Just 1. Doesn't change anything. So if I used to have 1 over 1 and I flip it, we still just have 1. So we're still right here for cosecant. Okay? You with me so far?
Yeah. What's this 1 over 1? Okay, cosecant.
Okay, cosecant is equal to 1 over sine of theta.
Oh, yeah. Okay.
So if sine of theta is 1, what's 1 over 1? Okay. All right. What about over here where sine of theta is, we'll go to where sine of theta is roughly 1/2. When sine of theta is 1/2, what's cosecant? 2. So it's up here. Similarly, sine's also 1/2 one here, so it's also 2 up here. And as sine of theta gets really, really close to 0, as we divide by a really small number, like 0.00001, what does that equal?
A really large number?
A really large number. That equals 10,000, right? So, as sine gets closer and closer to 0, this thing shoots off to infinity. You see that? Okay. So, what it roughly looks like, we have asymptotes here because we can't ever reach infinity, obviously. And we have an asymptote over here. And cosecant looks like this.
Is that what it's called?
Cosecant.
No,
Oh, this?
yeah.
Asymptote.
Asymptote.
Asymptote. It's something that the function approaches but never touches. It's an asymptote. Similarly, if we look at this part of the function, we are going to get the exact same thing. It's going to come down through that point and back down. And then back up here, we're going to get the same thing. It's going to go through and go like that. And we're going to get a similar thing down here. And it continues on its merry way. You with me? Now, better pictures of these are in your book. So you can look in your book to see the pictures of these. But that's what it's going to look like. Sine and cosecant. Now, if I were to graph cosine and secant, it's the exact same picture, but shifted this way pi/2.
Yeah.
Okay, so I'm not going to bother with that one. And now we'll move on to tangent. And once again, your book has pictures of all these that you can reference. Let's draw tangent over here. So, tangent now of theta. Remember what tangent of theta is. It's equal to sine of theta over cosine of theta. And we'll draw this one more zoomed in and try to get more points in here. So I'll make pi all the way out here. I'll make minus pi all the way out here. Try to get some half decent points in here. Minus pi/2. And we'll also have pi/6.
Pi/3.
Well, kind of want to get pi/3. Here, let me put the force in here as well. So, let's get the force in here, and then we'll also get the, try and get a lot of points for a unit circle. Maybe this will be enough. This is 3 pi force. This is pi force. This is
Negative pi force.
minus pi force. No, maybe some more points still. Should have zoomed in more. This is minus 3 pi force. Let's fill some points around here really quick. We'll just do this one really dense and not the rest. Here's pi/6, and here's pi/3. Okay? And then this should be enough to give us a good start. Okay, so put some points up here. 1, 2, 3, minus 1, minus 2, minus 2. Keep in mind that it's often the case when we graph that this axis and this axis are not on the same scale.
What do you mean not on the same scale?
Here's 3.14. Well, I guess it might be happen to be kind of close on this.
Okay.
So that's what I mean. Okay. So now let's plot this in. So we need to do sine over cosine at a bunch of points. So we'll make a little t-chart here. We'll do our thetas here and our tangent of thetas here. Okay. At 0, what's tangent of theta? It's sine over cosine. What's sine at 0? 0. Cosine at 0?
1.
0 over 1?
0.
0. With us? Okay, let's look at pi/6. Pi/6. What's sine at pi/6?
Half.
Yeah.
Can you trust that? Alright, so we got 1/2.
That's right.
What's cosine of pi 6?
Root 3 over 2.
Root 3 over 2. So we've got that ratio, or 1 over root 3, or root 3 over 3. Good?
Why did you times cosines by 3?
Okay, let's do some algebra real quick. This is 1 over root 3. Now multiply top and bottom by 1, or root 3. But multiply the whole thing by 1.
Oh, I see.
Okay. Now let's do pi fourths. What's sine of pi fourths?
Root 2 over 2.
Root 2 over 2. What's cosine of pi fourths?
Root 2 over 2.
Root 2 over 2. What's the ratio?
1.
1. Wonderful. So at pi fourths we have 1. And then finally, let's do pi thirds. What's sine of pi thirds? Root 3 over 2. What's cosine of pi thirds?
1/2.
1/2. Take the ratio. What do we get? Root 3.
Yep.
Okay, so let's try and plot these roughly. So we've got 0. At pi 6, we've got root 3 over 3. I don't have a good idea in my head of what that roughly is. It's got to be less than 1 though. Root 3 over 3. Oh wait, that's exactly right there. Now I remember. Okay, pi fourths is 1. And then pi thirds is root 3, which is going to be between 1 and 2 somewhere. Who knows? And then pi halves. Let's think about pi halves. Let's do that one. What's sine of pi halves? 1. What's cosine of pi halves?
0.
0. 1 over 0. Uh-oh, it doesn't work. But notice, as sine gets really, really close to 1, so when we were at 0.999 here, cosine was really close to 0, which is 0.001. And it gives us bigger and bigger numbers.
Okay.
Does that make sense? So this gets closer and closer to infinity, not quite. So we have an asymptote here. Follow that? Okay. And if we were to do the same thing except for over here, the only difference is all our numerators would have been negative as opposed to positive. Because now sine's down we're in the fourth quadrant. Does that make sense? So it's going to be the exact same thing except for we're coming down this way. So we're going to have our same asymptote over here. The function's only going to be going down. And now what does the function look like? The function looks like this.
So it'd be called an odd graph, is that right?
Yes, this is odd. This is odd, sine is odd, and cosecant is odd, and cotangent is odd. And then cosine and secant are even. So 2 are even, all the rest are odd.
Okay.
Which ones are these? How is cosecant odd?
Cosecant, odd. It's symmetric with respect to the origin.
Oh. So it doesn't actually have to pass through. That makes sense.
So the only ones are cosine and secant are the only evens. The rest are odd. Okay, and then cotangent, if we were to graph cotangent instead of tangent, it follows the exact same pattern that this one does. The only difference is it looks roughly like it shifted pi halves and then we flip them all. Because, hold on, let me finish graphing this some more. If we continue, since the function just repeats, so we come over here to 3 pi halves, we would just repeat the same pattern over and over again, because sine and cosine just keep on repeating as you go around and around the circle. So this, we get another one like this. Same thing, and another one over here. So it does these over and over and over again, right? Cotangent is the exact same thing, except for shift at pi halves, so it doesn't cross the origin.
In the negative direction?
Shift at pi halves back this way. Yep.
Okay.
And then flip all these. So cotangents are going this way instead. That's no difference.
Except that that's at the origin.
Yeah, except for now shift it. That's what I mean. Shift them all back pi halves. And then instead of them going up this way, they just say go up this way or down this way, however you
So
want to
it'd
say
be
it.
going through the asymptote.
No, the asymptote shift as well. It's a completely new graph. I'm just trying to give you intuition for what it looks like without drawing it.
Okay.
So if we draw it just very roughly, sketch the cotangent one, here's the origin, here's an asymptote at pi, here's an asymptote at minus pi, they look like this. That was terrible. But I think you get what I'm saying.
Yeah.
And then the y-axis acts as an asymptote as well.
From 0.
Huh?
Yeah. The origin is
The y-axis acts as an asymptote. Yes.
asymptote.
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 Yes. Okay. So that's the graphing of those functions. Now what we're going to focus on is trig identities, your trig identities. And we'll prove as much of these as we can. Well, as much as seems useful. Now remember, probably going to say this 100 times, you have a textbook, use your textbook, look at your textbook, read your textbook, it covers all the same stuff I cover. The only difference is a lot of people put a lot more thought into it instead of teaching something on the fly, and on top of that, they have nice graphics. You know? So your textbook's your friend. Can't overstress that.
Doesn't ask my questions though.
It does. It really does. But you got to keep reading and studying. And yes, it will answer your questions. You can learn from just a textbook. That is possible.
There's a lot of work, you don't find your answer.
Okay. So now let's go over the first basic trig identity. Going back to our unit circle. Here's our unit circle. This is 1. This is x comma y. Here it is, at some angle theta. This distance on our rectangle is x, this distance on our rectangle is y. Using our crazy Pythagorean theorem, we get
X squared plus y squared equals 1.
now, what is x in terms of trig functions? What is that x coordinate?
It's the cosine.
Cosine of theta, right? So cosine of theta squared plus
Sine of theta.
sine of theta squared, wonderful, is equal to 1. Now, we hate with a passion throwing parentheses in math when we don't have to. And so, no one actually writes it like this. They write cosine squared of theta plus sine squared of theta. And that is also what I will do.
Okay.
But it's saying square the whole function. This is shorthand for this. We're just super lazy. So this is the way you'll always see it. Make sense?
Mm-hmm.
Okay, so that is our first trig identity. Cosine squared plus sine squared is equal to 1. Maybe as we do the identities, I'll come stick them over here on the board. Note for your test, you are allowed a sheet of paper, a sheet of notes on your test. So you can write down all your identities and stuff like that. That's pretty reasonable thing to do so that you have them on your test.
Okay.
You're just not allowed to calculate on your test.
How big is the paper?
You'll have to show me. Don't go get a poster. Keep your own life easy. So we have cosine squared of theta plus sine squared of theta is equal to 1. That's our first trig identity. Okay, next trig identity. Maybe I'll just write out what the ones that we're going to do so I can reference them without looking at my calculator or my laptop, and then I'll just prove them one at a time. So the next one we'll prove is that 1 plus tangent of theta is equal to secant squared of theta, and then we'll prove that 1 plus cotangent of theta, cotangent squared of theta, is equal to cosecant squared of theta. And then we'll prove that, this one needs a little bit more room for it, we'll prove that cosine of alpha plus beta, when we're adding two angles together, is equal to cosine of alpha times cosine of beta, this one should be minus sine of alpha, times sine of beta. And we'll prove that sine of alpha plus beta is equal to sine of alpha times cosine of beta plus sine of beta times cosine of alpha. So So that will be a nice little kickstarter for us. Let's see some of the usefulness of some of these real quick. These two, just other identities are useful like this, but let's explain why these ones are now so useful. Notice on your unit circle, you only had so many identities memorized, right?
Yeah.
We memorized just a few points. This one enables us to talk about a lot more angles now that we might not have otherwise been able to talk about. So for example, if I were talking about pi 6, so we know what happens at pi 6, we know what happens at pi 4s, but what happens at the sum of those angles? So when we add those together, we get 5 pi 12s. What's the coordinates of 5 pi 12s? What does this thing look like at 5 pi 12s? When we add these two together. That's what these identities give us. So you can just plug it in here and notice, you know how to calculate now. So we're saying that the cosine of 5 pi 12s is equal to, since 5 pi 12s is just the sum of these two things, let me take it all the way back from the beginning. Or I'll just do one more step here. Cosine of 5 pi 12s is equal to cosine of pi 6 plus pi 4s. With me so far? And then we can just use this identity right up here to see what that equals. So that's equal to cosine of pi 6 times cosine of pi, oops, that's supposed to be fourths. Cosine of pi 6 times cosine of pi 4s minus sine of pi 6 times sine of pi 4s. Right?
Okay.
That's just using this identity. We haven't proved this identity yet. I'm just showing why this identity is useful and this is useful. And now we know how to solve this thing.
Is that a circle of times?
Oh yeah, that's a times. I do dots instead of x's. So times, yes. Okay, so now we know how to calculate all these values. What's cosine of pi 6? Root 3 over 2, right?
Mm-hmm.
Yeah.
Times cosine of pi 4s, root 2 over 2. Minus sine of pi 6, 1/2. Times sine of, yep, there we go. Now you can combine this all together. We can say it's going to be the square root of 3 times 2 gives me 6 over 4 minus 1 times root 2 is just root 2 over 4, which is equal to root 6 minus root 2 over 4. That's what it is. So that's the x-coordinate at this point.
And now we can do the sine as well, right?
Yep, and you can do the same thing for the sine.
Okay.
So oftentimes the angle that you need to work with, you might say, I don't know how to work with that angle. But maybe there's some clever, tricky way that you can express it as a sum of two angles you already know. And then work with it. And that becomes easy. A little bit of work, but the hard part's going from here to here. That's the hard part of problems like this. From there on out, it's just plugging in what you already know. So that's why these are useful. So we'll start checking these out, proving them. Let's start with the next one. Okay, so I'm trying to prove that 1 plus tangent squared is equal to secant squared. And we're just going to write out exactly what this is. 1 plus tangent squared of theta is equal to 1 plus tangent squared of theta. Do you remember how I define tangent of theta?
Sine over cosine.
I define it as sine of theta over cosine of theta. Right?
Yeah.
So I'm just going to make that substitution. So this is sine squared of theta over cosine squared of theta. Follow the substitution there?
Mm-hmm.
Notice that was squared, so I need a squared numerator and denominator. Okay, get a common denominator. We get cosine squared of theta plus sine squared of theta. I'm multiplying this one top and bottom by cosine squared, so I can get it all over cosine squared of theta. Follow the algebra there?
Mm-hmm.
Okay, now look. What do we know about cosine squared plus sine squared?
Equal 1.
How do you know that? First identity, right? So this is equal to 1 over cosine squared of theta, which, 1 over cosine, don't we have something for that? What is 1 over cosine of theta? That's our definition of secant of theta.
But with the square.
Okay, so let's do this one more time. 1 over cosine of theta, we can rewrite it like that, squared, which is the same thing as secant squared of theta. All that? Yep.
How did 1 plus sine?
Multiply top and bottom of 1 by cosine squared. So now we get cosine squared of theta over cosine squared of theta.
Multiply top and bottom.
Yep. So 1, 1. This is still 1.
Oh.
You see that? And now they have a common denominator, so we can add it. So this is the same as this, is the same as that.
Okay. Oh. Oh, okay. Yeah, I got you now.
Cool. Anything else? Alright, let's do the next one. Next one's going to be almost identical. I don't even know what we're doing, but why not?
Good. Little exercise on it.
Alright, so cotangent squared of theta, 1 plus cotangent squared of theta is equal to, what's cotangent?
Cosine over sine.
Cosine over sine. So we have 1 plus cosine squared of theta over sine squared of theta, right? Multiply 1 top and bottom by sine squared to get a common denominator. So now we're going to have sine squared of theta plus cosine squared of theta all over sine squared of theta, which is equal to, what's the numerator? 1 over sine squared of theta, which is equal to cosecant, cosecant squared of theta. Cosecant is, I'm spelling out the word instead of using the symbols. Cosecant of theta is equal to 1 over sine of theta. Right?
Yep.
Okay, so we prove that. Alright, these next two, we need to draw a couple triangles now. The reason it's called trig. The bigger I keep my picture, I think the easier it will be to see. Oop. Draw just like a quarter of a circle in here real quick. Okay. So what I'm going to do is, we'll do dotted line, call this angle alpha, and then we'll do dotted line, actually this one's going to be solid because it's going to be one of my triangles. You'll see why I'm doing this solid in a second. But anyways, this angle right here is beta. And so this whole angle is alpha plus beta, right?
Yeah.
And so by the way, this is 1, we're on the unit circle, so the radius here is 1.
Okay.
So what are we after? I'm trying to find the x and y of that coordinate. That's what we're after. Look, this is the x coordinate at the angle alpha plus beta. This is the y coordinate at alpha plus beta.
Yeah.
And I need to show it's all this. That's what I'm trying to show.
Okay.
So I'm trying to find the x and y coordinate at alpha plus beta. Does everyone understand how if I find this x and this y, I just barely prove these two?
Yeah.
If I show that they're equal to this. Because whatever this x is, we already know x is equal to cosine at that angle, which is alpha plus beta. And I already know that y is equal to sine at that angle, which is alpha plus beta. Okay? So I'm trying to finish these two. You with me so far? Okay. So, going to draw a couple triangles here. First one I'm going to draw, and have a little ruler here. Maybe we can keep this looking. It's barely too short. I'm trying to draw a right angle down to this line. That's what I'm trying to draw. So I'm trying to make this, I'll make this line solid now, so you see the triangle. A right triangle. So drop the line down from here to this line, wherever they meet, so that's a right angle. With me? Okay, now I'm going to do a similar thing, dropping a right angle down to this line. So this is a right angle. Good? And then we'll draw a dotted line down like this. And one more thing we'll do is we'll draw a dotted line from this vertex over here. And then this is the picture we can work with. So drawing all these, notice that this is still a right angle as well. Okay, so let's fill in some information that we know. Do the side picture over here. If these two lines are parallel, and I draw a line that slants through it like that, and I know that, let's see which one we have. If I know that this angle right here is 60 degrees, how big is this angle right here? 60 degrees, right? If these two lines are parallel. With me? Okay, notice that this line, even though my picture's lying, and this line are parallel. Because that's a right angle and that's a right angle. So these two are parallel. So if this angle's alpha, then this angle right here is also alpha. You follow that? Okay. So this angle right here was 90 degrees. Let me make sure everyone can see. This angle is 90 degrees, right? This portion of it is alpha. So this portion of it is 90 minus alpha. That's this portion right here.
Okay.
You with me?
Yeah.
Now, if this is 90 degrees, and this portion's 90 minus alpha, what's this portion? Alpha. Remember, the sum of all the angles in a triangle have to be
180.
180 degrees. And 90 plus 90 minus alpha plus alpha is 180.
Yep.
With me? Okay, so we got the alpha there, and I'm going to erase some of this because now it's just noise. Let me get rid of that. Now let's get started plugging in things that we actually know. Okay, so looking at this biggest triangle out here, I know that this side length right here is what? What's this side right here? Here's beta.
What is it?
Y.
Sine of beta?
Sine of beta, wonderful. So this is sine of beta. And what's this distance right here?
Cosine of beta.
Cosine of beta, perfect. Cosine of beta and sine of beta. Let's see now. Now looking at this small triangle right here, I need to find the length of this side. I don't think I care about the length of this side, but I do need to find this length right here. So what's this length right here?
Cosine of alpha. Or do I have that wrong?
Remember that for any triangle, so if I have any right triangle whatsoever, with any angle here theta, and with any hypotenuse r, what is this distance?
Cosine.
R cosine of theta.
R.
It's only cosine of theta in the special case where we're talking about where the hypotenuse is 1. So this was 1 sine of beta, and this was 1 cosine of beta. You with me?
Mm-hmm.
But in general, it's r cosine of theta and r sine of theta. Follow that?
Yep.
Okay. So once again, oh, we don't have the hypotenuse of that thing.
Yeah, we do.
No, cosine of beta is this whole thing. So I can't ask you that. Oh, we can say what this distance is with this angle. So looking at this angle, what's this distance?
Sine of alpha times.
R sine of alpha, right?
Yeah.
We're looking at this triangle right here.
Oh. I thought you were talking about.
Okay, looking at this triangle up here,
Mm-hmm.
R is sine of beta.
Yeah.
This height, this is the height of the triangle, right? When we're looking at the triangle this way, is R sine of alpha. Or in other words, R sine of alpha. You follow that? Because the hypotenuse on this small triangle is sine of beta.
Okay.
You with me?
Mm-hmm.
Okay. Now let's get some easy ones real quick. What's this distance right here? This whole distance right here is cosine beta. Maybe put that on the outside so that you remember.
Sine of alpha.
This is cosine beta. So what is this distance?
That's cosine.
That's
of alpha
cosine.
times cosine.
No, it's
Beta
r
times
cosine.
cosine beta.
Right, R cosine alpha, or where R is at.
Mm-hmm.
Because that is the hypotenuse of the right triangle we're talking about. So R cosine alpha. Right? And now this height is
It's r cosine.
R cosine or sine alpha. Follow that? Okay, we got that distance, we got that distance, we got that distance. Okay, we're missing this one and then we're good. So what's this distance now?
It's
R times cosine
sine
of
B.
R cosine alpha, where R is sine of beta.
Yeah.
So, right like this, I guess. R cosine alpha.
Okay.
Okay, so we got all the points we need. Now let's write out what each of these are. There's these pictures so we can find it out. Now notice that y is this whole distance. It's however high this thing is, right?
Yeah.
And this distance is the same as this distance plus this distance,
Yep.
Yeah.
right? So I'm just going to add this distance with this distance, and that's the height. So this distance right here is cosine beta sine alpha. So this distance right here is cosine beta sine alpha. I'm just going to flip those around and write sine of alpha times cosine beta. Same thing though, right? So that's this distance, plus this distance gets me all the way up there. This is sine of beta times cosine alpha, plus sine of beta times cosine alpha. That's that one.
Yeah.
Okay, now let's write out what the top one is. I'll rewrite it down here. Running out of space up there. Cosine alpha plus beta is equal to. Now notice that this distance, the x coordinate is this distance, right?
Yeah.
And this distance is the same as this whole distance minus this portion,
Okay.
which is this.
Yeah.
So I'm going to take this distance and minus this distance to get the x. So now this is equal to, I'm going to write the alpha first, cosine alpha times cosine beta. That was our big distance, minus our small distance. And I'm going to write the alpha first, minus sine of alpha times sine beta. Good?
Yeah.
All right. So there are your, probably the hardest proofs that we need to do. Now I'll get to some simple proofs. So your next proof is going to be that, let's just write these up here real quick. We're going to prove that sine of 2 theta, sine of 2 theta now, is equal to 2 times sine of theta times cosine of theta. And I'm going to prove that cosine of 2 theta, cosine of 2 theta actually has a couple of equal to. Cosine of 2 theta is equal to cosine squared of theta minus sine squared of theta. But it's also equal to, I don't have these other ones memorized. Do you remember what it is? If it's 1 minus 2 cosine squared or cosine squared minus 1. I think it's this. I'll have to double check these. It's also equal to 2 times cosine squared of theta minus 1. And it's also equal to 1 minus 2 times sine squared of theta, I think. The author only lists the first one, but we're going to prove the law of cosines, and so you need these for the half angle identity, so you need these. So I don't know why he doesn't have them listed here. If it doesn't come out that way, we'll catch it and fix them. Okay, so let's start with this one real quick. Nice and easy. So notice, sine of theta plus theta, well, let's start from the beginning. Notice that sine of 2 theta is equal to sine of theta plus theta. You follow that? Which is equal to, we have an identity for that. When we're adding two angles together, it's this. So it equals sine of my first angle times cosine of my second angle plus sine of my second angle times cosine of my first angle. Which is equal to, notice that and that are the same thing, so I have two of them. 2 sine of theta, cosine theta. Follow that? So that's that one. Now let's do this one. This one for the first one is pretty similar. So now cosine of 2 theta is equal to cosine of theta plus theta, which is equal to cosine of the first angle times cosine of the second angle minus sine of the first angle times sine of the second angle, which is equal to cosine of theta times cosine of theta is the same thing as cosine squared of theta, minus sine times sine is sine squared of theta, and there we are. That's the second one. Okay. Now, let's see. Starting with this equation again, because now I need to get this and this. So starting, once again, with the fact that I know that cosine of 2 theta is equal to cosine squared of theta minus sine squared of theta. With me so far? So we know that. I'm going to add 1 to both sides. You with me? Okay. So 1 plus is adding 1 to this side. Now I need to add 1 over here. See that 1 I added?
Yep.
Cosine squared plus sine squared is 1. First identity. So I added 1 to both sides. Good? Now, doing a little bit of simplifying over there, we get, and I'm going to write the cosine first here. So cosine of 2 theta plus 1, that's rewriting this side, is equal to, now we have cosine squared and cosine squared is 2 cosine squared of theta. You with me?
Mm-hmm.
Negative sine squared plus sine squared, those cancel out. Alright, so finally we get cosine of 2 theta is equal to 2 cosine squared of theta minus 1. Did I get it right?
Yep.
Yeah.
Alright, cool. Follow that? Now we're going to do the exact same thing, except for this time I'm going to subtract 1 from both sides. So I'll restart. So cosine of 2 theta, I know is equal to cosine squared of theta minus sine squared of theta. Now I'm going to subtract 1 from both sides. So subtract 1, and now I'm going to subtract cosine squared and subtract sine squared. You see how I subtracted 1 from both sides?
Mm-hmm.
Okay, cool. So now, notice this time the cosines are going to cancel out. And so I get cosine of 2 theta is equal to, oops, minus 1, is equal to, now we have minus 2 sine squared of theta. Right? Negative 1 there, but the cosines go out, so we have negative 2 of them total. Everyone follow that?
Mm-hmm.
Okay, now I'm just going to move the 1 to the other side. Add 1 to both sides, and so now we get cosine of 2 theta is equal to 1 minus 2 times sine squared of theta. Oh, there goes vacuum. Follow that? Yeah.
And we don't prove these at all in the homework, right?
I don't know why I gave you. You'll find out soon enough, though.
Okay.
Okay, so now we proved all those identities. Now we have our half angle formulas, and then we'll prove the law of cosines, and then we're done.
Done with the section, right?
Done with the section, done with the chapter, done for the day. Oh no, we need to talk about transforming sine waves. So same stuff we talked about last week, but we're close. We're close, we're close. Okay, half angle identities. Half angle identities. So the first one we're going to use the fact that cosine of 2 theta is equal to this. On the next one we're going to use the fact that cosine of 2 theta is equal to this. So doesn't matter which one we do first. We'll just do whichever one comes first. Okay, so cosine of 2 theta is equal to 2 times cosine squared of theta minus 1. Right?
Mm-hmm.
Okay, so now I'm basically just going to solve for the cosine of theta. That's all I'm going to do. So add 1 to both sides. I'm going to write this side first because typically we like the thing we're solving for on our side. So I moved the 1 over there and changed the order I wrote it. With me?
Yep.
Is anyone in algebra? Just plus 1 over here, and then change the order I wrote the sides simply because I want this side on my left. Okay, divide both sides by 2. Now we get cosine squared of theta is equal to cosine of 2 theta plus 1 over 2. Take the square root of both sides, and we get cosine of theta is equal to plus or minus the square root of cosine of 2 theta plus 1 over 2. That's one way that you'll see the half angle identity. The other way that people will sometimes write it will be like this. Let theta equal something like 2 alpha, or alpha halves. Now, let's see, 2 alpha. Something like that. So rewriting this exact same thing, then we get cosine of 2 alpha is equal to plus or minus the square root of cosine. No, I did that backwards. Let 2 theta equal alpha. That's what I want. So if 2 theta equals alpha, then 1 theta is only alpha halves. And then over here we have cosine of alpha plus 1 over 2. So here's how it's typically seen when people express it. The author's super lazy and just expresses it this way. But if you were to look up the half angle identity, most times it comes up something like this. So I'll write it like that over here. It's that the cosine of theta halves is equal to plus or minus the square root of cosine of theta minus 1 all over plus 1.
And isn't it 2 theta?
And typically we actually write the 1 first. So I'm going to write 1 plus cosine of theta all over 2. No, we got rid of the 2 a long time ago.
Yeah.
From here to here. Oh, if you're saying this, I just rewrote it. I replaced the alphas with thetas in the equation over here. Remember, they're just angle names, so that doesn't matter. If you were to scale up that angle and scale up that angle, it changes nothing. It's just you're deciding instead of theta counting for pi thirds, now I want theta to count for pi 6. Or whatever.
Okay.
Formula still the same. Okay, the one for sine, you do a similar thing, so I won't bother doing it. Sine of theta halves is equal to plus or minus the square root. The only difference is it's going to come out 1 minus cosine of theta all over 2. So to prove that one, you just start out with you start with cosine 2 theta is equal to 1 minus 2 sine squared of theta. You just start it out with cosine 2 theta equals this thing. And then comes out the same. Solve for sine of theta. Okay, so there's a bunch of your basic trig identities. If you want to just look up a table online and print it out, trig identities, and do it that way, that's perfectly fine too, and put that on your paper. But now we've proven all your trig identities. Last trig thing we need to prove is what's called the law of cosines, or some people call it the general Pythagorean theorem. So we know that the Pythagorean theorem only works with
Triangles.
right triangles. You can only use the Pythagorean theorem on right triangles. So, if you have a right triangle, and you know 2 sides of the triangle, you can always find the third side. Well, if you don't have a right triangle, is there still a formula that we can use so that if you know 2 sides of the triangle, you can still find the third side? The answer is yes, and it's called the law of cosines. So we'll prove it really quick and show you how to calculate it. So, pretend that's not a right angle. I don't know if it looks close to a right angle. I was trying to make something obviously not a right angle here. Didn't even think about that. Okay, so I'm going to call this point C. I'm going to call this point A. I'm going to call this point B. And I'm going to call this side length over here C. This side length over here B. This side length over here A. And we're going to call this angle here. It's just convention that you typically call the angle the capital letter of the side opposing it, or the capital letter of this. So this is also angle C. This is point C, this is angle C. You with me? Mm-hmm. Okay. So a scenario might come up where here we are, we know what A is, we know what B is, we know our angle, and our angle's not 90 degrees. Can I still figure out what C is? Is there something like the Pythagorean theorem? Right? If this was a right angle, then you instantly know that A squared plus B squared equals C squared. But we don't have that. So object of the game, trying to figure out what C equals. Well, we're going to find what C squared equals, but that's the same thing as C. Okay, so drop a horizontal down. Now I'm trying to drop that so both those are right angles with me there.
Yep.
So now we have 2 right triangles inside of our overall triangle. Now, I'm going to call this side of the triangle H. However, the distance from here to here, just the height of whatever that distance is. Okay, so since we have 2 right triangles, I know that internally I can use the Pythagorean theorem twice. So I know that, we also don't know what this whole side is. So this whole length is A. What should I call this portion?
A half?
A half.
No, it's not necessarily in half.
Oh,
Don't let my picture lie.
Yeah, equilateral triangles. I don't know if we did that.
Well, isosceles, but pretend that this wasn't such a nice picture. Pretend that where it starts. Here, let's just mess with this a little bit. Let's take that and just drop it like this. Okay. So there's C, and this is point B. Okay, no more confusion about that even close to 8 halves. Okay, A is the whole thing. I'm just going to call this portion right here X, just because it's a distance on the X-axis. Okay, And notice that this little distance right here then is what? If this is
A
A
minus
and this
X.
is
A
X,
minus X, yeah.
A minus X. Perfect. So this distance right here is A minus X. Everyone follow that?
Yep.
Okay, so now I'm going to use the Pythagorean theorem twice. I can use Pythagorean theorem with this side triangle and the Pythagorean theorem with this triangle. So the Pythagorean theorem with this triangle tells me what? It tells me that x squared plus h squared is equal to b squared, right? That's what Pythagorean theorem tells me here. What does Pythagorean theorem tell me here? Pythagorean theorem tells me here that a minus, well, so I have this, really quick, I'm just going to take this and solve for what h squared is. So h squared is equal to b squared minus x squared. Okay. Now, do the Pythagorean theorem with this triangle over here. So with that triangle, I know that a minus x squared plus h squared is equal to what?
C squared.
C squared. So that gives me that, if I solve this thing for h squared, I get h squared is equal to c squared minus a minus x squared. Follow that? So h squared equals this thing, h squared equals this thing, therefore this is equal to this. That's why we solve both those for h squared. So write that all in one go. So we got b squared minus x squared, or in other words, h squared is equal to h squared. C squared minus a minus x squared. Follow that? Okay. I should have written this the other way, because we're solving for c squared. So let me just rewrite the equation again. C squared is equal to b squared minus x squared, and then I'm actually going to add this piece over here, plus a minus x squared. Everyone follow the algebra of what I just did?
Yep.
I moved this piece over here, and then just flip my equation around so I can write my c squared first. Okay, so now we just need to multiply that thing out. So c squared is equal to b squared minus x squared plus a times a gives us a squared, a times minus x gives us negative ax, negative x times a gives us another negative ax, negative x times x is plus x squared. Okay, so c squared is equal to b squared, notice the x's go out, so we don't have that, plus a squared, minus, notice we have two of these, minus 2ax. You with me?
Yep.
Let's see really quick. So c squared is equal to, I'm just going to write a squared plus b squared minus 2ax. Okay, the only problem in our equation now is that x. We have no clue what that x is. Hypothetically, we knew our a, our b, and our angle, right? We need two sides in our angle, and our angle wasn't a right angle. We don't know what the x is. So what is x in terms of our angle?
Cosine of C.
Almost.
Times
Or cosine of theta.
Oh,
Or cosine of the angle.
Yep.
that's right. Oh, yeah.
You see it? Everyone see it? Okay, so this distance, x, is equal to r, the hypotenuse of the right triangle we're talking about, times cosine of the angle, cosine of c. Good? Plug it in, and now we get c squared is equal to a squared plus b squared minus 2ab times cosine of c. And there we go. That is the law of cosines. Now there's nothing special about the side we chose. So there's a bunch of different ways we can write this. We can write this as c squared is equal to a squared plus b squared minus 2ab cosine of c. We could have also written a squared is equal to b squared plus c squared minus 2bc cosine of a. And it would have been the exact same thing, and we could have also done b squared is equal to a squared plus c squared minus 2ac times cosine of b. All three of those equations hold when you have a general triangle like this. That one has a lot of drawing on it, we'll just redraw real quick. For any triangle, if this is A, this is B, this is C, and we call the point opposite the side length of that name A, B, capital C. I know that on a marker board. It's hard to tell the difference between a capital C and a lowercase c. Then this equation holds for all of them. And now, let's see why we call this the generalized Pythagorean theorem. Let's do this for a right triangle and plug into that formula and see what we get. So, I'll call this A, I'll call this B, I'll call this C. Now this side point right here is capital C. It's a right angle. This is capital B, this is capital A. With me so far?
Yep.
Pythagorean theorem. So let's plug into here. C squared is equal to A squared plus B squared plus, remember that's right angle, so minus 2 times A times B times cosine of what? 90 degrees or pi halves, whatever you want to call it. Right?
Yep.
What is cosine of pi halves?
It's
What is the x coordinate at 90 degrees?
0.
0. So this whole thing is 0. And you're left with A squared plus B squared equals C squared.
Okay. Can we do a can we do a rigorous one that isn't a right angle? Like actually put in points and whatnot?
Not really, because I don't know the numbers that will make it come out. Because I'd have to give you the angle and the sum. Oh, actually, yeah, we could.
So you have to know one of those two, or one of those three, two of those three values.
Might come out a little messy, but we'll see what happens here.
Okay.
So I'll call this angle right here pi thirds. Right? And we'll pretend that this right here is 5 and this is 6. And we'll just see what comes out. And we're trying to figure out what the side is. Okay. So we know that that side is. We'll call this side the side we're looking for. Just change up the variable names. We'll just call x. Looking at our formula, I know that x squared is equal to 5 squared plus 6 squared minus 2 times 5 times 6 times cosine of pi thirds.
Okay.
Just plug it into the formula.
Which is 1/2, right?
Yeah, so we get x squared is equal to 25 plus 36. What's that? Is that 61? Minus, we have 30 times 2 is 60 times 1/2 is 30. That came out really nice.
So
Oh, we still need square root it. Okay.
Yeah.
So it's 31. So x is equal to square root of 31 is this distance.
And you can do that for any triangle.
For any triangle.
Awesome.
Okay. So there's a lot of cosine. So that was all the trig stuff. Now the last thing you need to get comfortable with is how things change functions. Now we already talked about this last time. So I remember that we talked about what if we do c times f of x, how does that affect the function? 1 over c times f of x, how does that affect the function? Then we did f of x plus a constant, how does that affect the function? We did, I think that was the one we did first. So we did f of x.
f of c of x as well.
F of x plus, that was the second one. First one was f of x plus some constant, k. Then we did f of x plus k in there. Then we had that, then we had that. Then we had f of c times x. Then we had f of 1 over c times x. And we talked about what all these things do, right? So recap. This shifts your function up or down. This shifts your function left or right. Now a little bit unintuitive on this one. Minus shifts to the right, plus shifts to the left. So we did an example of that last week, videos online. This does what?
It stretches it vertically.
Stretches it vertically. This compresses it vertically. This compresses it horizontally. This stretches it horizontally. Okay, so the last thing the author does is introduces all these, in particularly with the sine function. Oh, I skipped over an inequality. We'll come back to the inequality, but show this really quick. So he says y is equal to, why does he put f instead of sine? Oh, first he writes it all in one go. So y is equal to a times f of b times x plus c plus d. Okay, so combining all these things into one messy go. The a here is stretching or compressing it vertically. Here's our function. The b here is compressing or stretching it horizontally. The c here is our shift. And the d here is shifting the whole function up or down. It's all these things combined in one go. There you have it. You with me?
Yep.
Okay, so now he says, in the special case when we replace this with the sine function, we have one way we like to write it. So y is equal to, typically when we're talking about the sine function, we use a capital A up front, called the amplitude of the wave. A times sine of 2 pi over, using a b here, which when we get to physics we'll replace that. B is equal to the period of the wave, that's how often it repeats, times x minus c. I think in physics we typically use an omega there, but that's the shift, and then that's the end of that, plus d. So first off, notice how this is almost identical to everything you see up here. The only weird bit right here is this 2 pi over b.
Yeah.
So the reason it's 2 pi over b is because what number do you plug in for b to make so that this term goes away? 2 pi, which is the regular period of a sine function.
Yep.
And if you make the period of a function smaller, let's get some intuition real quick. Which of these functions has a smaller period? This has a smaller period. The period comes quicker. Its period is shorter. Period is how long it takes to get back to where it started.
Okay.
Right? So this function starts repeating after every 2 pi. It goes down, up. Once it gets to here, it starts repeating. Your typical sine function. That's the period of the function. The period of this function, much shorter, right? Okay, so the smaller your period, the more it's compressed vertically. So your period's in the denominator here. So we want the period to do two things. We want it to go away when the period's exactly 2 pi, exactly what the sine function period is. So that's one thing we want to do. Two, rather than putting some random number in there to compress it, now we write it in terms of the period, and notice the period still compresses it exactly how we expect. The smaller the period, the bigger the number, the more compressed the function is. So it still functions the exact same way that does. We just wrote that term a little bit different so it's more convenient, so that means something, instead of plugging in an arbitrary number. So this still functions the exact same way as everything does up here. It's just this is a more convenient way to write this term.
Why do you subtract, do x subtract c instead of x plus c?
So that way it shifts how you expect it as well.
Right. So you add a
So
plus
now,
minus.
when you plug in pi halves, it shifts at pi halves.
Oh, okay.
So it also makes keeping track of how it shifts more convenient.
So it reverses.
So C now tracks the shift, B now tracks the period, instead of them just being numbers that you plug in. So everything still functions the same.
Okay.
Follow that?
Okay.
Okay, there's one more inequality that the author introduces. That's a useful inequality, and then we'll be done. I'll just write the inequalities out first, and then we'll prove them, but kind of fast and loose prove them, because once you see them, they're pretty clear. So he says, notice that the negative absolute value of phi is always less than or equal to sine of phi. It's always less than or equal to absolute value of phi. And then negative absolute value of phi is always less than or equal to 1 minus cosine, which is always less than or equal to absolute value of phi. So those are the two inequalities, and you can see this pretty easily on a picture. So try and draw just a quarter of a circle again. Very roughly, pick some random point on there, doesn't really matter where. Here's the angle we're talking about. Here's our phi. Now, this distance right here Well, maybe I'll just draw the triangle and then get you to see it. Okay, draw that triangle, draw this triangle. And we go ahead. Okay, and this is on a unit circle, so radius 1. So first thing to notice, on a unit circle with radius 1, what is this distance right here? From here to here.
Theta, it's not,
R theta.
R theta.
Yeah, if theta is in radians, the arc length is that many radiuses,
yeah.
right?
Okay.
So it's theta times r,
Which is just 1, right?
which is just 1. So this arc length is also theta, in the same units as your radius. It's theta.
So is theta always radians?
No, theta is just a variable.
So it's a little hard for us to know that was in there.
Oh, sorry. Yes. Always ask, are you talking about radians? If you're confused, what kind of angle? But almost always I'm talking about radians.
Okay.
Okay. So we have theta here. So this arc length right here is theta, right?
Mm-hmm.
Now let's focus on this right triangle over here for a second. With me? What's the height of this triangle? Sine of theta. Yeah, everyone see how she got that?
Yes.
Now, what's this distance?
It's
1.
1.
It's the radius of the circle.
Yeah.
Yep.
1.
This is a,
What's this distance?
Cosine theta.
What's this distance?
1 minus cosine.
1 minus cosine theta. So this distance right here is 1 minus cosine theta.
You say this is an isosceles triangle?
This is a right triangle. Isosceles means two angles are the same. Okay, so this length is sine of theta. This length is 1 minus cosine theta. Now, last thing I need to do is name this distance right here. You okay with me calling that r?
Sure.
Now, notice that this is always the case for this picture. Sine of theta is always less than or equal to r, right? This length of the triangle cannot be bigger than the hypotenuse.
Yep.
Okay, is less than or equal to theta. The straight line is always shorter than the curved path to get to the same point.
Yeah.
See that? Now, if we would have done a negative angle as well, if we had a negative angle, then the only difference is our arc length would have been, need an absolute value on there.
That's why you put it the
So sine of theta is always captured from above by theta, right? And then sine can also be negative, so when it's negative, it can't ever get more negative than negative absolute value sine theta.
Yeah.
Make sense?
Yep.
So that's the first inequality. The second inequality, very similar thinking. Notice that 1 minus cosine of theta is always less than or equal to r, for the exact same reason, is always less than or equal to theta. The absolute value, and that gives us this inequality.
Why is it less than or equal to? Why not just less than?
Think about the case where it's 0.
Where the
Where this point, where theta is 0.
0 degrees,
Yes, or 0 radians.
0 radians.
Yeah, then it's 0 is equal to 0 is equal to 0 is equal to 0.
So you have to do it just for the case of 0.
Yes. Good?
Yep.
I was a little lost how that right triangle, that one where it's 1 minus cosine theta.
Okay, let's redo it. This distance is
1, that's right.
1. This distance is,
You could say 1.
this is theta. Look at this right triangle over here.
Okay.
So this portion is just cosine of theta. Same reason as this portion is just sine of theta.
Okay, no, I'm with you now.
Okay, so then the remaining piece over here is just 1 minus cosine theta.
Oh, gotcha. Okay.
Yep.
I'm with you.
Anything else? Okay, so the section after this section, so that finishes off this section. The next section is completely focused on how to use your calculator, walking you through using your graphing calculator. Now, you will not need a graphing calculator for this class. I gave you a couple problems in that section to make sure you know how to use your graphing calculator. it's good for you to get a graphing calculator and use a graphing calculator. Now, while you won't need them in this class, it will be nigh into impossible for you to solve any physics problems without one and without knowing how to use it. So even though in this class, for calculus, you're not going to have your calculators on the test, you're not going to be able to use your calculators. Maybe I'll let you write at the end, I don't know. We'll see. You still need to be using your calculators. So you use your calculators on your homework, make sure you know how to use your calculators, start practicing with your calculators. In that section, just take your calculator and just go through the example problems and the homework problems, and I think you'll have a good foundation for all the tools you have in there to use. And then graphing calculators. I don't know if any of you have heard of a website called YouTube. They've got a tutorial for anything you want up there. You're trying to do something on your graphing calculator, go to YouTube, search it, and there will be someone there who shows you exactly how to do that thing you're looking to do. So if you have a TI-89 and your book's walking you through on how to use a TI-84, the book's going to tell you what they're doing. You just take that exact thing, how to, whatever it is, on a TI-89 on YouTube. Someone will walk you through it. Tons of resources. So there's no point in me showing you how to use each of your individual calculators. That's just a waste of time. Because I just have to figure it out same as you watching YouTube videos.
I have software, Microsoft Mathematics, that does a lot of that stuff. I'm sure that.
Yeah, any graphing software works fine. But if you don't have something, you're going to be in trouble come physics.
So you're saying read the section and then do the
Yeah,
whole
just
problems like it?
make sure you got your calculator, go through, do the example problems, and then I only gave you like 2 or 3 homework problems
Oh, okay.
for that section. So that whole section is just about your calculator. So that's it for new material. That's the end of the lecture. Rest of class you have to start with homework and ask me any questions.